Okay, this video is going to be about the dot product. Just the beginning, we're going to define what the dot product is and then look at a few of its properties. So we already have a couple of arithmetic operations that we do with vectors. We have vector addition, which is just component-wise for vectors of the same length, and we have scalar multiplication. So this new idea of the dot product, and you can see its name comes from the fact that we use that dot between the two vectors to represent that we're going to be doing the dot product. Okay. The other thing you realize is that this dot is floating, in the middle of the line. It's not like down here like a decimal point, so please don't write it that way. Okay. And so then the question is, well, what exactly do you do? The dot product. Well, with these two vectors, what we would do is you pair up the components. You pair up the first component, that's a 2 in this vector, and a -1 in this vector, and you multiply them. Okay? And then you take 3, the second component in the first vector, and the 5, the second component in the second vector, and you pair them up and multiply them. Okay? And then you add the results. So we'd have 2 times -1 is -2, and 3 times 5 is 15, and when you add them, you get 13. And that is the answer to this very first dot product question we've looked at. Now you can do it for vectors certainly of larger size. Here's a three-dimensional vector and 2 of them. We're going to dot them together, but the process is exactly the same, right? We pair up the corresponding elements. So we pair up the 1 with the 0, that becomes our first term. 1 with this -2, that becomes our next term. And the -5 with the -2, that becomes the third term. We do all that multiplication now, right? And the addition, and we have 8. Okay. So, in case you like something a little more formal, here are the definitions for the dot product in both 2 and 3 dimensions. Really, the third dimensional one looks exactly like the 2-dimensional one, just with an extra term tacked on the end. But you see that both definitions of the dot product give you this basic idea that you pair up components, multiply them. Okay? Each of the corresponding components gets multiplied with the corresponding component from the other vector, and then you add all of those products up, and you end up with the answer to dot product. Okay? Some assorted facts to know about the dot product. First of all, it goes by other names. It is also called the scalar product or the inner product. You see the scalar product is a especially good name, I think, for it because it reminds you that the output, okay, of a dot product, the answer is a scalar, a number. Okay? So you take 2 vectors, okay, but your answer is a scalar. Okay? It's interesting. So far, what we've learned, vector addition, scalar multiplication, right? The inputs were vectors, okay? The outputs were vectors. Okay? In order for the dot product to be defined, both vectors had to be the same length because you're doing this pairing up of corresponding elements, just like you did again in vector addition. And so it's undefined if the vectors aren't the same length. Okay? And there's nothing magic about 2 and 3 dimensions. We could have a 4-dimensional dot product, an 18-dimensional dot product, any finite number, and you just would extend the definition exactly the same way. Okay? But certainly in this class, we are going to focus on and stay most of the time in 2 and 3-dimensional space. So before you continue with this video, I urge you to hit the pause button and work out these 3 examples. And once you get done, you can go hit the play button, and you will go to the next page of this slideshow, which will show you the answers. Okay, so there are the answers, -2, 19, and 10. There's really all that's going on right here, right, is multiplication and addition. So if you don't have the right answer, go check your arithmetic. You may have been a little too fast in your mental arithmetic. And then the third one, with the one with the I, J's, and K's in it, I realized there was one that was, there's a missing component, so a 0 in there somewhere. To make sure that you took that into account, okay? And paired up the I's with the I's and the J's with the J's and the K's with the K's. Okay. Well, again, so far it just seems that we've made up this new kind of multiplication called the dot product. But as mathematicians, certainly once we make up something, we like to see what kind of properties it has. Does it have properties that we're familiar with from other things that we've worked with, like the real numbers? Okay? And it turns out the commutative property of multiplication, which we love, okay, does hold for the dot product, that A dot B does indeed equal B dot A. And I've written out a little proof here for it, just in the two-dimensional case. You could certainly, after you look at this, see how you could extend it to the three-dimensional case. We'll save a little writing here by just doing it in 2D. So, okay. Now, the thing I should point out, when you're trying to prove something that is an equality, we're used to so much in the math we do. When we see an equal sign, right, we're trying to solve that equation. We're trying to find the value of some variable here. We're not trying to do that here. We're trying to prove a fact. Okay, so we can't take this, right, and work on it from the beginning like we would do if we were solving an equation. We have to take one side or the other and show that you can logically get to the other side. So I've taken the left-hand side here, A dot B. Just used the definition of the dot product to write it out, right? In the 2D case, right? There's an A sub 1 and an A sub 2, right? We're dotting that with B sub 1 and B sub 2, right? The definition says, okay, that means pair up the corresponding components, multiply them, and then add all of those results. That's what I've done here. And then go from this line to this line here. Notice what I've done is take advantage of the fact that these are all real numbers, right? And I know the real number multiplication is commutative, so I've switched the order of that real number multiplication in both of those products to put the B term first and the A term second. And when it's written like that, well, that's what the dot product of the B vector first and then the A vector second would look like, which is, of course, B dot A. Okay? So since I started with A dot B, did a bunch of things which were equal to it, each time I'd use the equality using some property or the definition of the dot product, and I got down to B dot A. Okay, so A dot B must equal B dot A, and that's what I've stated my conclusion here with the little triangle of dots that we typically read as therefore. Therefore, A dot B equals B dot A. There are other neat properties of dot product. Here's a list of 5. Number 2 is the property that we just wrote the proof for. Okay, and in this one, A, B, and C are vectors, are all in boldface, and C is a scalar. So it's right. So there's a C. That's a vector here. Number 4, we also have a C floating around that is just a scalar. Okay? So as you can see, we have something here in number 3 looks like a distributive property. Number 4 shows how a scalar interacts with the dot product. And basically, you can see here what it's telling us is we can do that scalar multiplication times A, we could do it times B, we could do the dot product first and then do the scalar multiplication. It doesn't matter. And then 5 tells us what happens when we do a dot product with a 0 vector, and it makes sense that we would get 0 here because we'd have the first component, where every component of the 0 vector is 0. We'd pair it up with whatever was an A, and we'd get 0 plus 0 plus 0 in the 3D case. Notice that this is the scalar 0. That's the 0 vector, right? A vector with however many zeros you need to be of the correct length, whereas this is the actual scalar number 0, that thing in the number line that separates the positives from the negatives. I've left out number 1. It's what happens when you dot a vector with itself, and the answer is you get the square of its magnitude. And that's a useful little fact that we'll use in some proofs further down the line in this class. Right. So in conclusion, you should be able to go back to that last slide and prove the 4 proofs, the 4 properties that when you haven't done proofs, where you should be able to use the proof for commutativity as a template and kind of see how to step through each of those proofs, okay, to prove those properties. And then I hope that the burning question you have now is, okay, what does this dot product mean? Okay, we have geometric meanings for a vector addition, scalar multiplication. We seem to have made this notion of multiplication up out of thin air. Does it have a meaning? Of course, the answer to that is yes, but we'll have to wait for another video for that.